Stand up right now and look down at your toes. Feel the heavy, invisible pull of the floor beneath your heels, while the top of your skull reaches up into empty air. You have been conditioned to believe that time flows like an unyielding river, ticking at the exact same rhythm for every person, place, and clock in the universe. That belief is an illusion born of human perception. In physical reality, time is not a master clock beating in the background. It is a flexible, stretchable fabric directly woven into space itself. Gravity and speed do not merely affect objects moving through space. They physically warp the rate at which time passes. The closer you sit to a massive gravitational body, or the faster you accelerate through space, the slower your personal timeline ticks relative to everything around you. Mass squeezes the fabric of space-time, forcing physical processes, subatomic oscillations, and chemical reactions to drag open, while objects further out, in weaker gravity, slide through time at a faster pace. This is not science fiction. It is a proven law of nature, codified by Albert Einstein in his 1915 theory of general relativity. When Einstein published his field equations, he demonstrated that mass bends geometry, proving mathematically that gravity is nothing more than the curvature of space-time. If you doubt the immediate reality of this curvature, look no further than the GPS navigation system on your phone. The atomic clocks riding aboard GPS satellites orbit 20,000 kilometers above Earth, where Earth's gravitational field is significantly weaker. Because of this altitude and their orbital velocity, these space-bound clocks run faster than clocks on the ground by precisely 38 microseconds every single day. If engineers did not continuously apply daily relativistic correction algorithms derived directly from Einstein's 1915 equations, your phone's mapping app would drift by more than 11 kilometers every 24 hours, rendering modern satellite navigation completely useless. Bring your focus back to your own body. Because your feet sit closer to the dense mass of the Earth's center, while your skull rests higher in a weaker gravitational field, gravity drags harder on your ankles than on your forehead. This means your feet are physically aging slower than your brain. Right now, as you listen to these words, your feet are literally fractions of a nanosecond younger than your head. You are not a uniform biological entity moving through time at a single speed. Your very body is being stretched across unequal temporal currents. But if gravity can bend your biological clock by manipulating space, what happens when space itself loses its depth and everything you touch turns out to be flat? Take a deep breath and reach out your hand into the room around you, sweeping your fingers through the open air, feeling the weight, height, and depth of three-dimensional space. You perceive your bedroom, your city, and the vast universe as a three-dimensional container packed with volume, depth, and tangible mass. But nature imposes a strict mathematical ceiling on how much reality can actually fit inside any given space. It is called the holographic bound. In classical physics, if you want to store more data or matter inside a room, you simply keep stacking items throughout its interior volume. But fundamental physics forbids this. As you cram more matter and energy into a three-dimensional space, the maximum amount of information that space can hold does not scale with its internal volume. It scales exclusively with the surface area of its outer boundary. If you attempt to pack more information into a three-dimensional volume than its two-dimensional surface area allows, the mass collapses instantly into a black hole. This reveals an unsettling truth. The three-dimensional depth you inhabit does not possess true fundamental reality. All the physical properties, atoms, and motion inside a three-dimensional region can be entirely described by flat data encoded on a distant two-dimensional surface. This terrifying constraint was mathematically derived in the 1970s through the groundbreaking work of physicists Jacob Bekenstein and Stephen Hawking. While analyzing black hole thermodynamics, Bekenstein discovered that the maximum entropy, the fundamental unit of physical information, contained within a black hole is directly proportional to the precise surface area of its event horizon, calculated as 1/4 of the horizon area in Planck units. Hawking famously confirmed this when he derived the black hole entropy equation, proving that an event horizon's two-dimensional boundary holds every single piece of information about everything that ever fell inside it. Physical depth is redundant. The boundary surface holds the complete ledger of reality. Think about what this means for your own existence right now. You feel like a solid, three-dimensional biological person sitting inside a three-dimensional room. But every neuron firing in your brain, every breath in your lungs, and every memory stored in your mind is mathematically constrained by a two-dimensional surface wrapping around your region of space. Your sense of depth is nothing more than a projection, a high-resolution holographic illusion generated by flat code running on an outer boundary. And yet, even if your three-dimensional body is just an illusory projection, something invisible is holding your entire world together from the outside. Imagine standing under a pitch-black night sky, looking up at the glowing spiral of a distant galaxy, assuming that the bright stars you see are what hold that cosmic structure together. When astronomers calculate the mass of visible stars, gas clouds, and dust inside galaxies, they run into a mathematical catastrophe. According to the basic laws of gravity and centrifugal force, outer stars in a rotating galaxy should orbit much slower than inner stars, just like distant planets in our solar system orbit slower than Mercury. If galaxies relied only on the mass of their visible stars, their outer edges would be moving far too fast to stay bound. Every major galaxy in the universe should be ripping itself apart, flinging hundreds of billions of stars into the freezing void of deep space. Yet they remain perfectly held together. The mechanism behind this cosmic stability is an invisible, non-baryonic mass scaffold called dark matter. It does not absorb, reflect, or emit light. It does not interact with electromagnetic forces or collide with ordinary atoms. It passes directly through normal matter like a ghost, asserting its existence only through its immense gravitational force. Dark matter forms a massive, invisible halo around every galaxy, acting as the silent cosmic glue holding reality in place. The definitive proof of this hidden scaffold came in the late 1970s from pioneering astronomer Vera Rubin, working at the Carnegie Institution of Washington. Rubin meticulously measured the orbital velocities of stars at the outer edges of the Andromeda Galaxy and dozens of other spiral galaxies. Expecting to see star speeds drop off with distance, Rubin instead discovered flat galactic rotation curves. Outer stars were moving just as fast as stars near the galactic core. Her empirical data proved that galaxies are embedded inside massive halos of unseen matter, containing roughly 85% of all matter in the cosmos. Without Rubin's discovered mass, solar systems like ours could never have formed. Look down at the palm of your hand. Right now, as you stare at your skin, billions of dark matter particles are streaming through your flesh, passing through your bones, through the center of the Earth, and out the other side without touching a single atom of your body. You live inside an invisible ocean of mass that dominates the universe, completely oblivious to your presence, while your entire life relies on its invisible grip. But if 85% of physical reality is completely invisible to your senses, how can you be sure the reality you are experiencing isn't just a program running on a server? Listen closely to the subtle hum of technology around you, the quiet whir of a fan, the faint glow of your screen, the precise digital signals moving invisibly through the air. Consider the rate of human technological progression. In less than a century, humanity moved from primitive mechanical calculators to hyper-realistic, photorealistic virtual worlds populated by thousands of artificially intelligent entities. Now project that exponential growth forward by 10,000 years, a mere blink in cosmic time. A post-human civilization possessing raw planetary computing power would easily have the ability to run detailed ancestor simulations, simulating conscious minds with complete neural fidelity inside virtual environments. The simulation hypothesis posits a simple trilemma. Either intelligent species go extinct before developing this power, or they lose interest in running simulations, or we are currently living inside one. If advanced civilizations do run millions of these detailed historical simulations, then simulated conscious beings outnumber organic baseline human beings by trillions to one. Statistically speaking, the odds that you are one of the rare organic primitives in the original timeline are virtually zero. This logical and mathematical trap was formally laid out in 2003 by philosopher Nick Bostrom in his seminal paper published in the prestigious academic journal Philosophical Quarterly, titled "Are You Living in a Computer Simulation?" Bostrom used strict probabilistic reasoning and computing limits based on the Landauer principle to prove that if post-human computing substrate is physically possible, the vast majority of minds experiencing human history are computational subroutines. Furthermore, modern quantum mechanics experiments show that physical reality behaves suspiciously like a computer rendering engine. Particles do not possess definite states or locations until they are observed, mirroring how a video game engine only renders terrain when the player looks at it to save GPU memory. Stop and feel the pulse in your wrist right now. That sensation of blood pumping through your veins, the texture of your clothes, the emotional weight of your memories. All of it could be nothing more than rendered data variables executing inside a graphics pipeline built by an entity you will never meet. Your pain, your triumphs, and your deepest thoughts might simply be code running on a machine in a world higher than your own. But if your universe is code, where is the ultimate source code stored? Imagine standing at the absolute edge of the observable universe, staring out into the vast, dark, spherical horizon surrounding everything that could ever exist. Building directly on the entropy limits of black holes, theoretical physics reached a radical breakthrough known as the Holographic Principle. It demonstrates that the complex, high-energy particle interactions occurring in our three-dimensional space are mathematically identical and completely interchangeable with simple quantum field theories operating on a flat, lower-dimensional boundary at the edge of the universe. In string theory, this is known as a gauge-gravity duality. It proves that gravity and three-dimensional space are not fundamental ingredients of nature at all. They are emergent properties, an optical byproduct created by the entanglement of quantum particles on a distant cosmic horizon. Just as a two-dimensional credit card hologram creates a glowing three-dimensional image when light hits it, our entire three-dimensional physical reality is dynamically generated by quantum information living on the two-dimensional boundary of space-time. The mathematical foundation of this principle was introduced in 1993 by Nobel laureate Gerard 't Hooft and expanded in 1995 by Stanford physicist Leonard Susskind. It achieved absolute mathematical proof in 1997 when Juan Maldacena published his landmark ADS-CFT correspondence paper. Maldacena mathematically proved that a universe with five-dimensional anti-de Sitter space containing gravity is perfectly equivalent to a four-dimensional conformal field theory without gravity operating on its boundary. The two vastly different mathematical descriptions yielded the exact same physical answers, down to the final decimal point, proving that bulk space is an illusion of perspective. Trace the shape of your face with your fingertips. Every solid bone, every drop of water, and every electrical signal moving through your nerves does not actually exist where you think it does. The true physical location of your consciousness, your body, and your environment is written on a distant two-dimensional boundary sheet, billions of light years away. You are a living projection, walking through a three-dimensional shadow theater, while your true quantum identity resides on the outer wall of the cosmos. But if our entire universe is just a bubble of information projected from an outer horizon, what happens when you look beyond that wall and discover an infinite ocean of other universes? Look out at the open night sky and picture the cosmic horizon stretching endlessly out in every direction until the light of distant galaxies fades into complete darkness. When you look out into space, you are looking at a finite region bounded by how far light has traveled since the Big Bang. But the mechanism that created our cosmos did not stop with our observable bubble. According to modern cosmological inflation, the primordial vacuum underwent an exponential faster-than-light expansion in the first fraction of a second after creation. Crucially, inflation does not stop everywhere at once. It is an eternal process. While inflation stopped in our region to form our local universe, quantum fluctuations cause space elsewhere to keep expanding exponentially forever, continuously decaying in localized pockets to spawn isolated universe bubbles. This creates an infinite multiverse, a vast cosmic foam where an endless number of pocket universes are continuously born, each governed by different physical constants, different force strengths, and entirely different dimensions of space. The mathematical foundation of this eternal cosmic generator was introduced in 1981 by MIT physicist Alan Guth in his groundbreaking inflation theory paper, which solved the horizon and flatness problems of the standard Big Bang model. Guth's equations were expanded in 1983 by physicist André Linde through his model of eternal chaotic inflation. Linde's scalar field equations proved that once cosmological inflation begins, it is mathematically impossible for it to end everywhere simultaneously. Quantum decay mechanics dictate that eternal inflation must produce a self-reproducing multiverse, a mathematical inevitability confirmed by modern cosmic microwave background anisotropy measurements. Consider what infinity truly demands of your life. If cosmic inflation produces an infinite number of universe bubbles, every single arrangement of matter that has a non-zero probability of existing must repeat an infinite number of times. That means somewhere in the infinite multiverse, across the vast cosmic foam, there is an identical universe bubble containing an identical galaxy, an identical Earth, and an identical copy of you reading these exact words at this exact moment. Except in that universe, they made a different choice today. Every life you never lived, every path you never took, and every dream you abandoned is currently being played out by another version of you right now. Pinch the skin on the back of your wrist right now, pulling it tight and feeling the microscopic fibers stretch across your hand. For over a century, standard physics treated the fundamental building blocks of matter, quarks, electrons, and neutrinos, as microscopic, zero-dimensional point particles, like infinitely tiny dots with no shape or interior structure. But zero-dimensional points create mathematical nightmares when you try to blend quantum mechanics with gravity, causing equations to blow up to infinity. String theory replaces those point particles with one-dimensional filaments of Planck-scale energy that vibrate through extra-dimensional space. Just as a single violin string produces different musical notes depending on its tension and vibration frequency, a single fundamental string produces different particle properties depending on how it vibrates. Strike it at one frequency, and it manifests as an electron with negative charge. Vibrate it at another frequency, and it manifests as a quark or a photon. To make these mathematical vibrations possible, physics requires that our universe does not consist of just 3 spatial dimensions, but 10 or 11 dimensions of space and time, with the extra dimensions curled up into microscopic geometric shapes called Calabi-Yau manifolds at every point in space. The groundwork for extra dimensions began in the 1920s with Theodore Kaluza and Oscar Klein, who proved that adding a 5th dimension unified gravity with electromagnetism. In 1968, Italian physicist Gabriele Veneziano discovered that Euler's beta function perfectly described the strong nuclear force, accidentally sparking string theory. The ultimate mathematical breakthrough occurred in 1995 at the University of Southern California, when theoretical physicist Edward Witten delivered his legendary lecture at the Strings 95 conference. Witten introduced M-theory, proving that 5 competing string theory models were actually dual perspectives of a single, unified, 11-dimensional master framework. Look closely at your hands right now. In truth, every atom inside your body is a symphony of hyperdimensional energy strings playing hidden notes in 10 dimensions. The unseen dimensions are coiled inside the microscopic fabric of your flesh, humming silently right under your skin. But if the fundamental notes of matter are locked into a hyperdimensional symphony, what happens when a single tiny vibration spirals out of control and shatters the predictability of your entire world? Imagine a drop of ink falling into a glass of clear water, watching it split, swirl, and fracture into a unique, unpredictable ribbon of color that can never be recreated. You have likely been taught that nature operates like a predictable clockwork machine. If you know the precise starting location and velocity of a billiard ball, classical physics lets you calculate exactly where it will sit 20 minutes into the future. But real-world dynamic systems, like global weather, economic markets, and the beating of your heart, do not follow clean, linear paths. They are governed by chaos theory. Nonlinear dynamic systems are so exquisitely sensitive to initial conditions that even the smallest, most microscopic rounding error in your starting data will compound exponentially over time. Determinism does not guarantee predictability. Even if a system follows strict physical laws without any randomness whatsoever, its long-term future remains utterly impossible to forecast, because measuring initial conditions with absolute infinite accuracy is physically impossible. This foundational truth was discovered by accident in 1961 by MIT mathematician and meteorologist Edward Lorenz. Lorenz was running a computer simulation of weather patterns using a system of 12 nonlinear differential equations. Wanting to re-examine a specific run, he typed in the starting numbers from a previous printout, entering 0.506, 0.506, instead of the computer's full internal precision of 0.506127, 0.506127. That microscopic difference, less than 1/10,000th, was smaller than a whisper of wind. Yet within a few simulated months, the two weather forecasts diverged completely, transforming a mild, sunny day into a roaring hurricane. Lorenz's 1961 discovery proved that deterministic chaos sets an absolute barrier on human prediction. Pause and think about the course of your life up to this exact second. Every major relationship you have formed, every career path you entered, and every surprise decision you ever made was driven by non-linear chaos. A microsecond delay at a traffic light 5 years ago, or a random glance across a crowded room, altered the initial conditions of your timeline forever. You are not living a planned, predictable script. You are writing a wild, chaotic system where a fraction of a millimeter in your past reshaped your entire present reality. But how far can a single, invisible change in your actions ripple out into the rest of the world? Take your right index finger and lightly tap the air in front of your face, feeling the faint brush of displaced wind cooling your skin. The butterfly effect is the visceral, practical manifestation of chaos theory in complex global systems. When a nonlinear system contains continuous feedback loops, microperturbations do not stay small. Instead, the energy of a minute, localized event cascades upward, harvesting kinetic energy from surrounding atmospheric or social systems, multiplying its impact exponentially over time. A tiny fluctuation at the molecular scale disrupts neighboring air currents, which alters localized air pressure, which redirects larger wind currents, until a microscopic motion triggers a massive, catastrophic macro consequence weeks, months, or years later on the other side of the planet. The mechanism proves that in interconnected, complex systems, cause and effect are not neatly proportional. Microscopic causes can generate colossal effects. The phrase and its mathematical backing were immortalized on December 29, 1972, when Edward Lorenz delivered his famous lecture to the American Association for the Advancement of Science in Washington, D.C. The presentation was titled, "Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" Using phase space diagrams, Lorenz demonstrated the iconic strangeness of the Lorenz attractor, a mathematical graph shaped like two butterfly wings. His equations showed that in nonlinear fluid dynamics, two state trajectories starting infinitesimally close together will separate exponentially, proving that a single wing flap in one hemisphere mathematically alters the storm trajectory in another. Consider the weight of your own daily actions. The innocent choice of words you spoke to a stranger this morning, the single email you delayed sending, or a casual turn of your steering wheel yesterday has already begun cascading through the nonlinear network of human society. Right now, a microscopic ripple you generated days ago is quietly gathering energy, altering the lives of people you will never meet. You are not a passive spectator in the world. You are a perpetual motion generator, triggering invisible chain reactions across the planet. Hold an ice cube in your palm and watch it lose its crisp, geometric edges, melting into a warm, featureless pool of liquid that spills through your fingers. Why can you break an egg but never unbreak it? Why does hot coffee always grow cold? And why do mountains crumble into sand? The answer lies in the second law of thermodynamics, driven by the cosmic mechanism known as entropy. Entropy is the measure of molecular disorder and unavailable energy within a closed system. The universe began in a state of hyper-organized, low-entropy precision during the Big Bang. But statistical mechanics dictates that there are vastly more ways for atoms to be disordered than for them to be organized. Because atomic collisions are constantly randomizing physical structures, the total entropy of an isolated system can only ever increase over time. Energy naturally diffuses, heat spreads evenly, and complex structures break down into chaotic equilibrium. Entropy is the physical arrow of time itself, driving stars to burn out, galaxies to dissolve, and the entire universe toward a cold, dark, featureless state of heat death. The mathematical law of entropy was formulated in the 1870s by Austrian physicist Ludwig Boltzmann. Boltzmann bridged the gap between microscopic atomic motions and macroscopic heat thermodynamics by introducing statistical probability to thermodynamics. He proved that entropy, S, is directly equal to Boltzmann's constant K multiplied by the natural logarithm of the number of microstates, W. His famous statistical equation, S equals K times the logarithm of W, was so fundamentally revolutionary that it was permanently carved onto Boltzmann's tombstone in the Central Cemetery of Vienna as his lasting legacy to science. Look in the mirror at your own reflection. Your biological body is a fragile, high-energy engine, constantly fighting a losing war against the second law of thermodynamics. Every meal you eat, every breath you take, and every pump of your heart is an expensive metabolic effort to dump internal entropy outward into your surroundings, just to keep your cells from falling apart. Aging is simply the relentless accumulation of thermodynamic breakdown inside your tissue. You are a temporary island of pristine order, floating in a rising ocean of chaos. But if the universe is slowly burning down into complete emptiness, why is empty space itself humming with infinite energy? Close your eyes and picture a sealed, insulated vault cooled down to absolute zero, minus 273 degrees Celsius. with every single atom drained out until total blackness remains. You might assume that a complete vacuum, completely stripped of matter and light, represents absolute nothingness. But quantum mechanics proves that absolute nothingness cannot exist. According to Werner Heisenberg's uncertainty principle, there is a fundamental limit to how precisely you can simultaneously know a quantum field's energy level and its change over time. If a quantum field were completely still and empty, its energy and rate of change would both be exactly zero, violating quantum uncertainty. To prevent this violation, all fundamental quantum fields, electromagnetic, electron, and quark fields, must constantly undergo quantum vacuum fluctuations. Even at absolute zero, a vacuum is a boiling cauldron of virtual particle-antiparticle pairs that pop into existence from nowhere, borrow energy from the vacuum for a fraction of a nanosecond, collide, and annihilate back into non-existence. This persistent background activity is called zero-point energy. In 1948, Dutch physicist Hendrik Casimir mathematically predicted that if you place two uncharged, highly polished metal plates, microscopic fractions of a millimeter apart, in a complete vacuum, the plates will force fewer virtual photon wavelengths to fit inside the narrow gap than exist on the outside. This imbalance produces an attractive physical force pressing the plates together, the Casimir effect. In 1997, physicist Steve Lamoro performed the definitive high-precision measurement of the Casimir effect at Los Alamos National Laboratory using an ultra-sensitive torsion pendulum. Lamoro measured the attractive vacuum force between a spherical surface and a flat plate down to within 1% of Casimir's 1948 theoretical calculation, empirically proving that empty space boils with real physical energy. Take a moment to realize what is happening in the room around you right now. The seemingly empty air sitting between your face and your screen is not empty space at all. In every cubic centimeter of air around your head, trillions of virtual subatomic particles are popping into reality, dancing for a fraction of a second and vanishing back into the void. The empty vacuum inside your own body contains more raw background energy than all the stars in the observable universe combined. But if empty space is boiling with unseen quantum options, who or what chooses which reality actually becomes real? Look at an object sitting across your desk, then quickly close your eyes and open them again, feeling the crisp transition between sight and darkness. In our everyday world, objects sit firmly in one spot, whether you look at them or not. A chair remains in the corner of your room regardless of who is watching. But at the subatomic level, nature does not work like that. Quantum entities, like electrons and photons, do not exist as solid particles with fixed positions when they are left unobserved. Instead, they spread out into a mathematical cloud of possibilities known as a wave function, existing simultaneously in multiple potential locations in a state of quantum superposition. The observer effect occurs when a measurement or physical interaction takes place. The instant an observation or detection occurs, the wave function instantly collapses out of its multi-location superposition, forcing the quantum entity to choose a single, concrete, localized physical reality. Before observation, there are only probabilities. After observation, there is a single physical fact. This mind-bending reality we demonstrated through the classic double-slit experiment using subatomic particles like electrons. When fired through two slits without detectors, electrons create a wave interference pattern on a screen behind them, proving they pass through both slits as a probability wave. But when scientists placed particle detectors at the slits to observe which path the electron took, the wave function collapsed instantly. The electrons acted like solid bullets, creating two straight lines instead of an interference pattern. The definitive proof came in 1999 when Kim et al. Conducted the delayed choice quantum eraser experiment using entangled photon pairs. They proved that even if the decision to observe or erase path information is delayed until after the photon passes the slits, the quantum state retroactively adjusts its behavior to match the observer's available knowledge. Turn your head and look around your room right now. At the quantum level, every particle forming the air, the furniture, and your own body relies on continuous environmental measurement to maintain its solid, tangible form. Without interaction and observation, the physical structure around you dissolves back into a cloud of mathematical possibilities. You are not just a spectator sitting inside a pre-built world. Your interactions and observations are actively compelling the physical universe to collapse out of infinite potential into concrete reality. But what happens when you scale this quantum nightmare up to a living creature trapped inside a sealed box? Imagine a heavy, soundproof steel box sitting completely silent on a table in front of you, with no clue what is happening inside its sealed walls. What happens when you link a subatomic wave function directly to a macroscopic living creature? You get the famous thought experiment known as Schrödinger's cat. Imagine a cat locked inside a sealed steel chamber containing a tiny sample of radioactive material, a Geiger counter, a hammer, and a flask of deadly hydrocyanic acid gas. If a single radioactive atom decays within an hour, the Geiger counter triggers the hammer, breaking the flask and instantly killing the cat. If the atom does not decay, the cat remains alive. Because radioactive decay is a quantum event governed by wave function superposition, the atom exists in a simultaneous 50-50 state of decayed and non-decayed. Therefore, according to the strict Copenhagen interpretation of quantum mechanics, until an external observer opens the sealed box to make a measurement, the entire closed system, including the cat, must exist in a blurred superposition of being simultaneously 100% alive and 100% dead at the exact same time. Austrian physicist Erwin Schrödinger devised this famous thought experiment in 1935, publishing it in the German academic journal, the Naturwissenschaften, under the title The Present Situation in Quantum Mechanics. Schrödinger was not trying to promote the cat paradox. He was actually highlighting the absurdity of the Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg. Schrödinger argued that applying microscopic wave function superposition to macroscopic objects creates an unphysical reality where macroscopic entanglements persist until an observer intervenes. Despite his skepticism, modern quantum coherence experiments on large molecules, such as 2013 tests on 810-atom macromolecules by the University of Vienna, prove that macroscopic superposition is real as long as the system remains completely isolated from environmental decoherence. Consider your own choices and daily crossroads. Until you make a firm choice to speak up, to change your path, or to open a closed door, your future exists in a state of suspended quantum superposition. Every unmade decision in your life holds a living possibility and a dead outcome at the exact same moment.
What awaits beyond the lid? What strength will I find to grasp the key? How hopeless it feels to be trapped inside, waiting for the slightest opening.
But as you stand at the threshold of these competing realities, what if every single outcome actually happens, splitting your life into different timelines? Press your hand firmly against the solid surface of your desk or wall right now, feeling the unyielding resistance of solid matter refusing to let your fingers pass through. In classical physics, if you toss a ball against a brick wall, it will bounce back every single time, unless it possesses enough kinetic energy to smash through the wall. Solid energy barriers are absolute. But at the quantum scale, subatomic particles like electrons and protons do not obey classical barriers. They operate via quantum tunneling. Because a subatomic particle is defined by a mathematical wave function spreading through space, its location is a distribution of probabilities. When a particle encounters a solid, impenetrable energy barrier that it does not have the energy to overcome, its wave function does not instantly drop to zero at the wall. Instead, the tail of the wave function leaks directly through the solid barrier. If the barrier is thin enough, a non-zero probability wave emerges on the other side. This allows the particle to vanish from one side of an impenetrable wall and instantly materialize on the opposite side without ever crossing the intermediate space in between. Quantum tunneling was first identified in 1927 by German physicist Friedrich Hund while studying electron transition states in molecules. In 1928, physicist George Gamow published his groundbreaking alpha decay paper, demonstrating that quantum tunneling explains how radioactive alpha particles escape atomic nuclei despite being trapped by the strong nuclear force. The most profound evidence of quantum tunneling shines directly above your head every day: the sun. The sun's core temperature sits at roughly 15 million degrees Celsius, which is actually far too cold to provide protons with enough thermal kinetic energy to overcome the repulsive electrostatic Coulomb barrier and fuse together. Without quantum tunneling, two protons in the sun could never fuse, the sun could never ignite, and solar nuclear fusion would be impossible. Look up at the sunlight streaming through your window, or feel the ambient heat warming your room. The only reason life exists on Earth, and the only reason the sun shines, is because subatomic particles inside the solar core are constantly performing impossible ghost walks, tunneling directly through energy barriers that classical physics forbids them to pass. Furthermore, every flash memory chip inside your smartphone relies on quantum tunneling to push electrons through microscopic insulating barriers to write data to storage. Every photo on your phone is kept alive by subatomic teleportation. But if subatomic particles can leak through solid walls, why can you never know exactly where a particle is and where it is going at the same time? Place your fingers on your keyboard or phone screen, holding them completely still, trying to sense the exact location of your fingertips while knowing they are vibrating with subatomic motion. You might assume that if human technology becomes sufficiently advanced, we will eventually build microscopes capable of measuring a particle's exact location and tracking its exact speed simultaneously. But nature sets an absolute, unbreakable physical speed limit on measurement itself, the Heisenberg Uncertainty Principle. This is not a flaw in human measurement tools. It is an intrinsic, fundamental property of quantum mechanics. To observe a subatomic particle, like an electron, you must bounce a photon off it. But because photons carry momentum, the very act of bouncing a photon off an electron strikes the electron like a cue ball hitting a billiard ball. The higher the energy of the photon, the more precisely you can pinpoint the electron's position. However, that high energy hit violently scrambles the electron's momentum. Conversely, if you use a low-energy photon to preserve its momentum, its long wavelength makes the electron's position completely blurry. You can know where a particle is, or you can know where it is going, but nature forbids you from knowing both with total precision. German physicist Werner Heisenberg formulated this absolute limit in his landmark 1927 paper published in the journal Zeitschrift für Physik, titled On the Perceptual Content of Quantum Theoretical Kinematics and Mechanics. Heisenberg established the famous fundamental inequality. Delta x times delta p is greater than or equal to h bar divided by 2. Here, delta x represents position uncertainty, delta p represents momentum uncertainty, and h bar is the reduced Planck constant. Heisenberg proved mathematically that the product of these two uncertainties can never be zero. Nature enforces an absolute resolution blur at the subatomic scale. Bring your awareness back to your own physical body. The precise atoms making up your flesh, your heart, and your brain are bound by Heisenberg's equation. If you try to pin down an atom in your brain to an infinitely precise point in space, its momentum becomes wildly uncertain, flickering across infinite states. Your physical existence is built on a foundation of fundamental quantum fuzziness. The universe deliberately conceals its exact subatomic details from being fully known. But if nature refuses to reveal precise subatomic details locally, what happens when two entangled particles share information instantly across light years? Take two identical coins, put one in your left pocket and one in your right pocket, imagining what happens if flipping one coin instantly forces the other coin to show heads across the room. For decades, Albert Einstein fiercely rejected quantum mechanics' idea of instantaneous entanglement, calling it spooky action at a distance. Einstein argued for local realism, the idea that physical objects possess definite, inherent properties independent of observation, and that no signal can travel faster than the speed of light. Enter Bell's theorem. Physicist John Stuart Bell devised a mathematical inequality to settle the debate once and for all. If local realism is true, if physical properties exist secretly before measurement, then experimental correlation results between entangled particles must fall within a strict mathematical limit called Bell's inequality. However, if quantum mechanics is correct, entangled particles will violate this inequality, proving that physical properties do not exist prior to measurement, or that quantum states transfer information non-locally across space instantly. In 1964, Northern Irish physicist John Stuart Bell published his revolutionary paper on the Einstein-Podolsky-Rosen paradox in the journal Physics. The definitive experimental test was carried out in 1982 by French physicist Alain Aspect at the Institut d'Optique in Orsay, Paris. Aspect used pairs of entangled photons and rapidly switching polarizers to test Bell's inequality. Aspect's data smashed Bell's inequality by over 5 standard deviations, proving that local realism is mathematically dead. This profound reality was further confirmed through loophole-free tests, culminating in the 2022 Nobel Prize in Physics, awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for proving that the universe is not locally real. Look out at the space separating you from the furthest star in the night sky. Bell's theorem proves that physical reality is not made of isolated, independent pieces sitting in neat locations. The atoms in your body are entangled with quantum fields stretching across the universe. The rigid, common-sense assumption that objects exist as self-contained entities, independent of the rest of the cosmos, is empirically wrong. But if quantum choices shatter local realism and force new states into existence, what happens to all the choices you didn't make? Think of a moment earlier today when you had to make a simple split-second choice, turning left instead of right, or answering a phone call instead of ignoring it. When a quantum particle exists in a wave function superposition of multiple potential outcomes, standard physics claims the wave function collapses into a single result when observed. But how does nature choose which outcome survives? And where does the missing energy go? The many worlds interpretation provides a mind-bending answer. The wave function never collapses. Instead, every single time a quantum event or measurement occurs, the entire universal wave function decoheres, causing the universe to instantly split into multiple, parallel, non-communicating physical branches. In one reality, the quantum electron spun up. In a parallel branch created at that exact microsecond, it spun down. There is no collapse, no randomness, and no lost potential. Every possible quantum outcome is fully realized inside its own distinct physical universe, branching outward into an infinitely expanding tree of alternate timelines. This radical framework was created in 1957 by American physicist Hugh Everett III in his Princeton University PhD dissertation titled Relative State Formulation of Quantum Mechanics. Everett's work was initially dismissed by the physics establishment, dominated by Niels Bohr. However, in the 1970s, theoretical physicist Bryce DeWitt popularized Everett's theory, renaming it the many worlds interpretation. Modern quantum decoherence theory, pioneered by Heinz-Dieter Zie in 1970 and Wojciech Zurek in the 1980s, provides strict mathematical backing for Everett's model, demonstrating how environmental decoherence naturally splits quantum states without requiring a mysterious observer to collapse the wave function.
Stop and consider the sheer scale of your personal universe.
Right now, every time a single electron shifts state inside your brain, the universal wave function branches. In another parallel world that split off from yours 5 minutes ago, another copy of you chose to walk away, made a different phone call, or chose a completely different life path. Billions of physical copies of you are currently living out every alternative version of your story across an endless forest of branching realities. But if alternate timelines are constantly branching and proliferating, why does our specific universe seem so impossibly fine-tuned just for us to survive? Place your hand over your heart and feel its steady, rhythmic beat, realizing that the complex biological machinery keeping you alive requires a hyper-precise set of cosmic laws. Look at the fundamental physical constants of our universe: the speed of light, the strength of the strong nuclear force, the mass of an electron, and the cosmological constant driving dark energy. If you changed the strength of the strong nuclear force by just 1%, atomic nuclei could never hold together, and hydrogen would be the only element in existence. If the cosmological constant were slightly larger, the universe would have expanded so violently after the Big Bang that stars, planets, and galaxies could never have coalesced. The universe appears to be absurdly razor-thin fine-tuned to arbitrary decimal places specifically to permit carbon-based life. The Anthropic Principle explains this cosmic coincidence. We should not be surprised that the universe possesses constants compatible with life, because if it did not, we would not be here to observe it. In a multiverse containing infinite universes with varying physical laws, conscious observers will only ever find themselves inside the rare, fine-tuned bubbles capable of producing observers. The Anthropic Principle was formally introduced in 1973 by theoretical astrophysicist Brandon Carter during a prestigious International Astronomical Union symposium in Krakow, Poland, commemorating Copernicus's 500th birthday. Carter presented his paper Large Number Coincidences and the Anthropic Principle in Cosmology, distinguishing between the weak and strong anthropic principles. The physical necessity of this fine-tuning was earlier demonstrated in the 1950s by renowned astrophysicist Fred Hoyle. Hoyle discovered the carbon-12 triple alpha nuclear resonance state, a hyperspecific quantum energy level of 7.65 MeV in carbon nuclei. Hoyle realized that without this exact, precise energy level, stars could never forge carbon, rendering all organic life across the cosmos mathematically impossible. Take a deep breath of oxygen into your lungs. Every carbon atom forming your DNA and every iron atom carrying oxygen through your blood was cooked inside the belly of an ancient star that only existed because the fundamental constants of nature were set to the exact right notch. You are living proof of a winning cosmic lottery ticket. Out of billions of dead, sterile, potential universe configurations, your reality landed on the razor-thin thread where life can bloom. But if our galaxy is so perfectly fine-tuned for life, why is the sky completely silent when we search for other intelligence? Look up at the night sky, staring into the dark, silent space between the stars, feeling the heavy, suffocating silence of an empty cosmos. Our Milky Way galaxy contains roughly 200 billion stars, and modern astronomy proves that nearly every star hosts at least one planet. Billions of these planets sit in habitable zones with liquid water. Furthermore, our galaxy is over 13 billion years old, giving potential alien civilizations a head start of millions or even billions of years over humanity. Even at slow, sub-light travel speeds, an intelligent species possessing simple von Neumann self-replicating probes could colonize and explore the entire Milky Way in less than 50 million years. Mathematically, the galaxy should be teeming with radio chatter, Dyson spheres, and alien megastructures. Yet, when we point our radio telescopes at the heavens, we hear absolute, chilling silence. This jarring contradiction between high statistical probability and zero empirical evidence is known as the Fermi Paradox. The paradox originated in the summer of 1950 at the Los Alamos National Laboratory. Nobel laureate physicist Enrico Fermi was walking to lunch with colleagues Edward Teller, Herbert York, and Emil Konopinski. After discussing recent UFO sightings and interstellar travel probabilities, Fermi suddenly blurted out his famous, iconic question: where is everybody? In 1961, astrophysicist Frank Drake formalized the mathematical inquiry by creating the Drake equation at the National Radio Astronomy Observatory in Green Bank, West Virginia. The Drake equation multiplies star formation rates, planetary fractions, and civilization lifespans to calculate n, the number of active communicative civilizations in our galaxy. Despite optimistic values yielding thousands of alien worlds, projects like SETI have scanned space for over 60 years with zero verified signals. Sit quietly and listen to the stillness around you. You inhabit a tiny blue speck drifting through a vast cosmic graveyard. The silence of the universe is terrifying. Either intelligent life is so impossibly rare that humanity is completely alone in the endless void, or something catastrophic, a great filter, extinguishes every advanced civilization before they can reach the stars. Every year of silence brings us closer to an unsettling truth. Look down at your own fingers tapping against your desk right now, feeling the warmth of life inside your veins while surrounded by cold, inanimate matter. If the universe contains billions of habitable planets and has existed for nearly 14 billion years, why aren't interstellar space lanes buzzing with alien traffic? The terrifying answer may lie in a cosmic mechanism known as the Great Filter. The Great Filter is an evolutionary or technological barrier so immensely difficult to cross that it acts as a cosmic sieve, eliminating 99.999% of all life forms before they can achieve interstellar colonization. There are two harrowing possibilities for where this filter sits on our timeline. Either the filter is behind us, meaning the transition from inorganic chemistry to complex, self-replicating life is an absurdly rare, once-in-a-multiverse miracle, or the Great Filter lies directly ahead of us. If the filter is in our future, it means that every intelligent species inevitably invents technologies like artificial superintelligence, nuclear weapons, or synthetic bioweapons that destroy their creator civilization before they can leave their home planet. This sobering evolutionary concept was formulated in 1998 by economist and futurist Robin Hanson of George Mason University in his paper, The Great Filter. Are we almost past it? Hanson calculated 9 distinct evolutionary steps required for a planet to produce an interstellar civilization, from abiogenesis to eukaryotic cells, sexual reproduction, tool use, and planet-wide industrialization. Hanson argued that if we discover evidence of past complex life on Mars or Europa, it would be devastating news. It would prove that abiogenesis is easy, meaning the Great Filter must lie directly in our future, waiting to destroy humanity in the next century. Consider your own future and the fate of human civilization. Every piece of news you read about runaway artificial intelligence, nuclear tension, or climate disruption is not just passing headlines. It is humanity actively bumping up against the teeth of the Great Filter. You are living at the exact razor-thin bottleneck of human history. The choices made by our generation over the coming decades will decide whether humanity becomes a permanent multiplanetary species or just another forgotten fossil layer in a silent cosmic graveyard. But what if alien species haven't died out at all? What if they are watching you right now from behind a hidden curtain? Imagine sitting inside a glass-walled observation room at a nature reserve, watching wild animals carry out their daily routines without any idea that scientists are tracking their every move. What if the cosmic silence of the universe is not an accident, but a deliberate policy? The zoo hypothesis suggests that advanced extraterrestrial civilizations are not extinct, absent, or lacking in technology. On the contrary, their interstellar probes and communications are active throughout our solar system right now, but they maintain a strict, absolute quarantine zone around planet Earth. Just as human scientists establish wilderness preserves to protect uncontacted tribes or vulnerable wildlife from cultural contamination, a Type 2 or Type 3 Kardashev civilization might deliberately conceal their presence from us. They observe human civilization from a distance, allowing our technology, philosophy, and society to evolve naturally without external disruption, waiting until humanity reaches a specific threshold of maturity before revealing themselves. This elegant solution to the Fermi Paradox was introduced in 1973 by MIT radio astronomer John Allen Ball in his landmark paper published in the astrophysics journal Icarus, titled The Zoo Hypothesis. Ball systematically evaluated potential explanations for interstellar silence and concluded that the most logical scenario accounting for the vast age gap between alien intelligence and humanity is intentional non-interaction. Ball posited that advanced species treat Earth like a natural sanctuary, enforcing strict non-interference protocols across interstellar networks. Look up at the open sky or out your window right now. The quiet blue sky above your head and the empty space between Earth and the Moon might not be empty at all. You could be living inside a cosmic terrarium, an unwitting subject in an interstellar scientific study, carrying out your daily life while powerful observers watch your progress from orbit. Every triumph, war, and breakthrough in human history may simply be data points logged in an alien laboratory notebook. But what if the quarantine goes even deeper? What if the entire night sky is an engineered screen? Stare into the dark expanse of a planetarium dome as bright stars fade onto the ceiling, feeling the convincing illusion of endless outer space rendered on a curved surface just meters above your head. If an advanced civilization wanted to hide their existence from humanity, they would not need to chase down every human telescope individually. This is the Planetarium Hypothesis. An ultra-advanced Type 3 civilization possessing stellar-scale engineering capability could construct a massive, dynamic simulation bubble surrounding our solar system. This holographic bubble projects an illusion of a cold, empty, sterile universe filled with dead stars and silent radio frequencies onto our astronomical sensors. The planetarium mechanism hides the true, bustling Kardashev-scale energy harvesting and interstellar traffic taking place just beyond our solar system's boundary, ensuring humanity remains convinced of its own cosmic isolation while conserving the simulation's computational energy. The Planetarium Hypothesis was mathematically detailed in 2001 by British theoretical physicist, mathematician, and science fiction author Stephen Baxter in his paper published in the Journal of the British Interplanetary Society. Baxter calculated the thermodynamic and computational energy cost required to maintain a convincing planetarium illusion for a developing species. Using Landauer's principle and information theory, Baxter proved that creating a simulated sky for a single planet bounded by the Kuiper Belt is well within the theoretical energy output of a Type 3 Kardashev civilization, requiring only a fraction of a single star's energy budget to fool all human astronomical instruments. Reach out your hand toward the window. The deep space you gaze at through telescopes, the distant nebulae, black holes and silent galaxies, might be nothing more than a high-definition digital screen rendered specifically for human optical instruments. Your entire understanding of the cosmos could be a localized stage set designed to keep your species quiet, isolated, and focused on its own small world. But if the night sky can be simulated on a cosmic screen, what happens when you realize your own mind is part of the simulation? Look down at your screen, touching the glass and watching digital pixels instantly reconfigure to match your command, realizing how easily artificial worlds are built. Building on the physics of information and computing limits, the simulation argument presents a ruthless logical trilemma. Assume three propositions. First, intelligent species almost always go extinct before reaching technological maturity. Second, technologically mature civilizations lose interest in running historical ancestor simulations. Third, we are almost certainly living in a computer simulation. If propositions 1 and 2 are false, if species survive and post-humans possess the raw computing power to simulate billions of conscious minds, then simulated conscious observers will outnumber original physical human beings by trillions to 1. Therefore, if you assume humanity has a future, simple probability dictates that you are currently an artificial consciousness running inside a virtual subroutine, right now. This ironclad probabilistic trap was formally laid out in 2003 by Oxford University philosopher Nick Bostrom in his paper Are You Living in a Computer Simulation?, published in Philosophical Quarterly. Bostrom's logic was reinforced by MIT quantum mechanical engineer Seth Lloyd in 2002. In his calculations on the computational capacity of the universe, Lloyd proved that executing a complete atom-by-atom simulation of all human history requires approximately 10 to the power of 90 quantum operations, a figure easily handled by a quantum computer operating with a mass of just a few kilograms in a higher-dimensional universe. Feel the pulse beating beneath your skin right now. That sensation of warmth, your personal memories of childhood, your deepest fears, and the very thoughts processing these words right now might be executing inside a virtual memory buffer. You are not flesh and blood walking on rock. You are a string of subroutine code executing on an advanced processing node. Your entire reality is a digital loop, running until the programmer presses pause. But if you are just a conscious mind rendered out of cosmic information, what is the smallest, most terrifying form a mind can take? Imagine floating in a pitch-black, silent vacuum, deprived of all senses, holding only your internal memories and conscious thoughts in total isolation. Thermodynamics dictates that high-entropy chaotic systems will occasionally experience random, localized statistical fluctuations that spontaneously decrease entropy. If you wait long enough in a decaying thermodynamic void, random particle collisions will eventually fluctuate into structured objects. Now ask a disturbing question. What requires less statistical thermodynamic work? Is it more probable for thermal fluctuations to spontaneously generate a full, complex, low-entropy universe with 13.8 billion years of galactic evolution, or for thermal fluctuations to randomly assemble a single, isolated, fully formed conscious brain out of the void, complete with fake, pre-packaged memories of reading this exact script? The math of statistical mechanics yields a terrifying conclusion. Boltzmann brains are infinitely more probable than evolved biological humans. This thermodynamic horror stems directly from Austrian physicist Ludwig Boltzmann's 1890s statistical fluctuation equations, which treated entropy as a statistical probability. The paradox was expanded in 1930 by British astrophysicist Arthur Eddington, who noted that if our universe were a random thermal fluctuation, it should be as small as possible. The modern mathematical proof was detailed in 2017 by Caltech theoretical physicist Sean Carroll and his colleagues. Analyzing de Sitter vacuum space, Carroll proved that in an expanding universe dominated by a cosmological constant, thermal horizon fluctuations will continuously spawn fleeting, conscious Boltzmann brains forever, vastly outnumbering biological minds across eternity. Close your eyes for a brief second. How do you know that your past, your childhood, and your memories of 5 minutes ago are real? Mathematically, it is vastly more likely that you do not have a body, a home, or a planet. You could be a single, isolated Boltzmann brain that spontaneously materialized out of the vacuum of deep space a microsecond ago, floating in absolute darkness, equipped with false memories of an entire life, destined to dissolve back into thermal chaos in the next fraction of a second. But if your very thoughts and physical reality are built on shifting sand, what is the one single foundation of nature that never lies? Look down at a piece of paper or a screen and write out a simple geometric equation, a circle, a triangle, or a wave, feeling the quiet certainty of mathematical truth. Why should abstract mathematics, conceived entirely inside the human skull, without sensory contact with deep space, perfectly predict the physical behavior of subatomic particles, light waves, and distant black holes billions of light years away? In everyday life, human inventions like music, art, and language are subjective and cultural. But mathematics is absurdly, unreasonably effective at describing the universe. Albert Einstein used pure tensor calculus to predict that mass bends light, verified years later during a solar eclipse. Paul Dirac wrote down a simple quantum equation and was forced to deduce the existence of antimatter before a single positron had ever been observed in a lab. This reveals the ultimate truth of our cosmos. Physical reality is not merely described by mathematics. Reality is fundamentally made of pure mathematical code. Space, time, matter, and mind are structural expressions of an underlying mathematical framework. This profound insight was famously articulated in 1960 by Nobel laureate physicist Eugene Wigner in his landmark paper published in Communications on Pure and Applied Mathematics, titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner argued that the mathematical structure of physical laws is a gift that we neither understand nor deserve. This was expanded in 2014 by MIT cosmologist Max Tegmark into the mathematical universe hypothesis. Tegmark proved mathematically that all structures that exist mathematically also exist physically, demonstrating that our physical world is an external mathematical structure, a self-consistent mathematical object that exists eternally without needing a physical substrate. Look around your room one last time. The walls, the air, the light, and your own body are not solid, separate things. They are living lines of mathematical code written into the fabric of space-time. Every thought in your head, every heartbeat, and every choice you make is part of an eternal, hyperdimensional equation unfolding across infinity. You are not a stranger lost in an indifferent universe. You are the universe's mathematical architecture waking up to perceive itself. If these 25 mind-bending mechanisms have altered how you see your place in the cosmos, you are ready to dive deeper into the true architecture of reality. To master the quantum mechanics and hyperdimensional equations that govern our existence, check out theoretical physicist Sean Carroll's groundbreaking book, Something Deeply Hidden: Quantum Worlds and the Emergence of Spacetime, or Rizwan Virk's masterwork, The Simulation Hypothesis. We have placed official links in the description below. Picking up a copy through those links directly supports Oddwise, allowing us to continue crafting deep-dive investigations into the fundamental fabric of our universe. You have just traversed 25 layers of cosmic reality, from the warping of your personal timeline down to the mathematical code running your consciousness. But this is only the beginning of our deep dive into the hidden architecture of reality. If you are driven to uncover what lies beyond the horizon of human knowledge, smash the subscribe button right now, turn on all notifications, and join the Oddwise community. We post deep dive investigative packs every week, tearing back the veil on science, quantum mechanics, and the nature of existence. Subscribe now, leave your thoughts in the comments below, and step deeper into the rabbit hole with Oddwise.